Hello, everybody. Today we'll talk about the speed of sound. Now, sound is a vibration that propagates as an acoustic wave through a medium. Sound waves are generated by a source of sound, for example, a loudspeaker or a human speaking. And as the source continues to vibrate the medium, the vibrations propagate away from the medium at the speed of sound. And the speed of sound is the distance traveled per unit time by a sound wave. The speed of sound in air at a temperature of 20 degrees, so room temperature, is about 343 meter per second. So at that speed, it can, sound can travel like 1 kilometer in 3 seconds or a mile in 5 seconds. And at 0 degrees, the speed of sound is about 331 meter per second. The speed of sound varies with different parameters. As you observed here, it does vary with temperature, but there are many more parameters. We'll discuss them in detail. So first, we have a medium. So sound waves need a medium to propagate. They cannot travel in a vacuum because vacuum is devoid of medium. So there are two properties in a material that determine the speed of sound. First is the elastic property and the second is the inertial property. Let's discuss about the elastic properties. Elastic properties define the stiffness of a material. For example, in solids, this is defined as the elastic modulus or the Young's modulus. The stiffer the material, the stronger is the interaction between the atomic particles and faster is the speed of sound. And in liquids, we don't have Young's modulus, but we have something similar, which is the compressibility represented by the bulk modulus. Gases are easy to compress as compared to liquids, and liquids are more difficult to compress as compared to solids, and solids are like most difficult to compress. Liquids and solids are often referred to as being incompressible. Under normal conditions, there are conditions where you can, but at room temperature, you cannot simply compress a liquid. It's incompressible. Based on the stiffness and compressibility of the material, it can be inferred that the sound waves travel slower in gases, faster in liquids, and fastest in solids. This is because solids are more stiff compared to liquids, which are more stiff compared to gases. So obviously, the speed of sound is fastest in solids, less, faster in liquid, and very slow in gas. The next is the inertial property. So density of a material is an example of inertial property. Now, the greater the density or the inertia of the atomic particles of the medium, the less responsive will they be to interactions between the neighboring particles, and slower is the speed of sound. Now, gases are less dense compared to liquids, which are in turn less dense compared to solids. So if you consider only density alone, sound will travel very slow in solids, faster in liquids, and fastest in gases. But if you observe around, or if you know already from high school, you know that sound travels, faster in steel, less faster in water, and much slower in air. It sounds contradictory, but it's not. It's because the stiffness and the compressibility effect outperforms this density effect. So, despite air being less dense, sound waves still travel slower because of the stiffness compressibility being low. Now, here are some equations. This is the equation for speed of sound in gases, which is square root of k over rho, which is bulk modulus of the fluid over density of fluid. Now, when I say fluid, it means both liquids and gases. So the speed of sound for solids is given by this equation, which depends on the bulk modulus, shear, Young's modulus, density, and Poisson's ratio. We'll actually be using this equation to determine the speed of sound in a solid. Also, we'll be using this equation to determine the speed of sound in liquid and gases. So there are certain effects on the speed of sound. The first is the effect of temperature. The speed of sound is directly proportional to the square root of temperature. So you can get this ratio as C1 over C2 is equal to square root of T1 over T2. So let's say if you know the speed of sound at room temperature and you wish to determine the speed at a different temperature, you can use this equation to determine so. So the speed of sound increases by 0.606 meter per second for every 1 degree Celsius increase in temperature, and conversely, if there is a 1 degree decrease in temperature, it's going to decrease by 0.606. So next is the effect of density and pressure. So the speed of sound in an ideal gas is given by k over rho, which we know, which k can also be interpreted as gamma times p, which is the adiabatic index times the pressure over the density. Now for air, gamma is 1.4. So as pressure changes, the density also changes proportionately such that the ratio p over rho is always constant. So the speed of sound is thus independent of both density and pressure because they both cancel out. So at high altitudes, although the density and pressure change, the ratio remains constant and there is no effect on the speed of sound. So let's say if you're at a very high altitude, but still you maintain this room temperature of 20 degrees C, the speed of sound would still be 343 meter per second, as if it was, on ground level. So let's try to use those equations to calculate the speed of sound in several mediums. So first, let's say we try to determine the speed of sound in water. So the density of water, as we know, is 1,000 kilogram per meter cube. The bulk modulus is this. At this room temperature of 20 degrees C, you input the values and you get, it's 1476 meter per second. Yes, it is. It's way faster than it's in air. The next is the speed of sound in ice. So the density is 916, the bulk modulus and shear modulus as mentioned. We input those values and we get 3890, almost 4 kilometer per second in ice. And ice is less dense than water, that's why it floats on water. So next is the speed of sound in hydrogen. So, put the density and the bulk modulus and we get it as approximately 1.3 kilometer per second. So to conclude, the speed of sound is the distance traveled per unit time by a sound wave. There are two properties in the material that determine the speed, the elastic and the inertial properties. And as the air pressure changes, the density also changes such that the ratio is constant and the speed of sound is independent of change in pressure or density. All right, thank you for watching this video. I hope you enjoyed it. Have a great day.